Hello, and welcome to this video focused on planning for instruction with the new science and engineering education standards for Utah. Now, before we can really talk about planning and instruction, we first need to come to a clear understanding of what we see science as to our students. I want you just to think about this for a moment and maybe jot some notes down if you need to about what do you really think that science is to your students. Not so much to us as the teacher, but to the kids. What is science to them? When I ask people this question, a lot of times I get things about it's a bunch of information they should know, or that they feel like it's a bunch of information they need to learn. Sometimes it's a discovery process. Sometimes teachers think that students see science as that exciting part of the day that they get to go to, or sometimes on the flip side, sometimes it's not that exciting time of the day. Sometimes it's, where we go and we learn a lot of information that we really feel is not relevant to our life. And so what we want to do is really keep that in the back of our mind, because when it comes to planning for instruction, that is a key, very, very important part of that. So we're going to look at a couple pictures here real quick as we get going through this. Now, what you see on the screen right now is these are the science and engineering practices that you've been learning about so far in your modules as you've gone through this course. And so we won't dive too much into those, but so far you should understand that these are the doing science kinds of things that, based on their name here, they need to be practiced. They need to be, students need to have time and chances in class to really practice these things and get better at them. Kind of like riding a bike. You need to get out on that bike as often as possible, and the more you do it, the better you get at it. Okay, so let's look at a couple pictures here real quick. Here's a little guy trying to put on his sock. He's having a very frustrating time of that, and just cannot get that thing on. Now, over time, he does eventually get the sock on. It does take him looking at an adult in the room putting their own sock on. It does take him trying multiple different ways of putting that on. But this entire time he's going through this process of trying to put that sock on his foot. I want you to think about the practices that you've learned about so far and ask yourself, what of those practices is this kid doing? Is he constructing an explanation on a really basic level? Is he analyzing and interpreting some data that he's been collecting qualitatively? Is he doing any of those things? Think about that for a little bit. Let's look at another picture. Here we have another kid trying to do a flip on a tramp, and as you can see, he's probably going to get hurt here in a second. Now, what you can't see is he's got a friend on the side of the trampoline that's yelling comments at him and arguing with him about what he needs to do. Because his friend is gathering qualitative data, he's gathering qualitative data in the air. They're both using that to come up with some sort of explanation of how to make this work and how to solve this problem that he seems to be in here. And so I want you to think about the situation of this kid trying to do this flip, doing it over and over and over and over and over again, coming up with different ideas about what needs to be changed in order for it to work each time, and then arguing about what needs to be changed with his friend over on the side of the trampoline. And every time he goes through this process, he gets a little closer and a little closer, and he gets rid of all the ideas that don't work. And he's getting closer to understanding what does work. So think about that. Think about that situation and think about these practices. Okay? Maybe just on a really basic level. Do you feel like those kids, those that were in those pictures, are doing any of these things? They're obviously not carrying out what we would consider in our classrooms to be a full experiment, but do you think they're doing any of these kinds of thinking? Do you think they're practicing being analytical about the way they observe and analyze the world around them? I would argue that they are. I would argue that they're doing quite a few of these things on a totally different level than what we usually see in our classrooms, but still doing some of these things. because these are not they're not one-shot kind of activities. These are practices. These are things that kids need to get better and better and better at. So when we think of what is science to our students, in the elementary grades and the lower levels here, science is very qualitative. It's very, let's look at this and observe the world around us and the natural world, and let's practice thinking about this analytically. Let's practice analyzing some data that we've gathered, even if it's just qualitative. And let's ask some questions about the world and see what we can find going on in the world. So at the elementary level, this stuff is awesome and fun, and it really creates a spark for these kids, and they're starting to really understand and examine phenomenon of the world around them and trying to understand that. And yes, they are learning some content, they're learning some ideas, but they're learning it in the context of doing science and practicing and getting better at learning about the world around them. Now, our job in the K-12 education system our job is to give them experiences to build these skills year after year. So as we go from kindergarten through 6th grade and on up through junior high, and depending on what district you're in, are moving all the way up into the high school levels and going into college, we should be giving them experiences where they get to develop these skills. And as they get older, we start moving from qualitative based skills to more quantitative based skills. And we start really refining our measurement. We start really refining the questions that we're asking. We start controlling our experiments. We start getting better and better and better at doing science and about analyzing the world around us. But these skills have to be built over time. And that's the whole idea behind the practices, and a huge push behind these new standards that we have coming out. Is these standards focus on what the kids should know, but also what they should be able to do. So where we want to know, we want these skills to be growing. We want to know what should the kids be able to do at specific grade levels in order for us to keep this progression happening to where they're getting better and better at doing science, and their tools become more sophisticated, their questions become more detailed, their level of analysis and computational thinking goes off the charts. And by the time they get to college, we want them to be ready to be able to use technology and math and really be specific in what they're looking at, and really be able to learn about the world themselves through these skills that they've built and be able to solve problems. And so when we're thinking about what is science to our students, it's a wide range of things, but it's definitely not just a bunch of information. It is information. We do need to teach these kids the content, but in the context of practicing doing science, so that they grow these skills from year to year and get better and better at it. So, another piece of that we've talked about during this course so far is the cross-cutting concepts. Not only do we want students to learn the material, we also want them to learn that material in the context of practicing doing science and becoming better scientists, so being able to actually learn about the natural world themselves through this process. But we also want them to be able to see these larger concepts that cross all of the different disciplines of science, and there are ways for us to kind of look at the world and analyze it. So no matter what topic we're looking at, we want these kids to be able to look at different phenomena if it's appropriate in terms of systems and system models. We want them to see the energy and the matter within those systems and how that moves around, because regardless of what discipline we're in, these things exist. And by students, when they look at this phenomena in terms of these kind of bigger, simpler ideas, they start to see these in all of their disciplines and can start to kind of analyze the world in a much more structured way. If we can start to get them to look at systems in terms of stability and change, or look at organisms or building structures, or whatever they're looking at in terms of its structure and function. And so we really want to have this kind of cross-cutting um, way of looking at phenomena, while also getting the kids practicing those analytical ways of thinking, those scientific ways of thinking, while they're going through the process of learning the information and the learning about phenomena in different disciplinary areas of science. And so that's really the bringing it all together of these three dimensions of science that we keep talking about, is that, if we can get the kids to see the world and to learn in our class from all three of these aspects, but all kind of interwoven together, it brings a really rich experience for the students. So, at the elementary level, a lot of our laboratory space might look like this. And as our skills get more refined, like we were talking about, and as we get better at those practices, we start moving to more of lab spaces that look kind of like this. Because we do start to get more quantitative, and we get a lot more analytical, and we get a lot more specific, and we need to start getting better tools and better technology, and we need to be able to measure more accurately as we build these skills. So, I think we would all agree that science is a way for us to learn about the world. And in the beginning, it's very, very basic, like possibly putting a sock on, or observing a tree, or seeing a flower come up and grow. And so it can be really basic. But over time, we get better and better and better at it. And as educators, it's our job to give these students those experiences to get better at it, and to help them along that pathway of getting better and better at learning about the world. So what we want to kind of pose here is that a really great process for taking kids through learning about the natural world is through gathering, reasoning, and communicating. So gathering information, reasoning that information, and then also communicating that information out to other people. But we also want to look at this new aspect of these standards. These standards are bringing a whole other piece to it, and that's the engineering side. These are now the science and engineering standards, not just the science standards. And so let's look at what that's all about. So when you think about science, if you think of some things or some terms that might describe that, sometimes you'll think of observations, controls, experiments, variables, a tentative base of information, a process that you run through. It's iterative, and of course it's awesome. Now engineering, when people kind of say, what do you think engineering is? A lot of teachers that I talk to say, well, it's problem solving, designing, building, has to do with technology, tons of math, a process, iterative, and of course it's also awesome. So similarities between these two, where they kind of connect with each other, is they're both processes for learning and solving problems. They both use this kind of iterative approach where we learn information and that helps us build on or learn more information. So this cycling. So in science, a lot of times, we do multiple experiments to get a better understanding of some process or phenomenon. And in engineering, you do the same thing. You do this brainstorming process to try to figure out the best solution to a problem. And they're both awesome. So what we're kind of seeing with similarities here is it seems like they kind of have this symbiotic relationship between each other, where science is learning about the natural world and understanding information and understanding phenomena happening around us. But then we take that information and we use it to solve problems. And so there's this back and forth between these two. So we have science, learning about the natural world. We use that information to then solve human-based problems. A great example of this is we learn about the water cycle, and we learn about how water moves around the planet. And if we leave it there, the kids think that's great and all, yay, water cycle. But where's the relevance to their day-to-day life, and where do we connect it to their actual life? And that's where the engineering comes in. Engineering now brings this direct relevance to the student's life, because now we can talk about the water treatment and the water capture process, and how do we actually use the water cycle to find out where that water will be, set up systems to capture that water and clean the water and send it out to people to use at their houses. How does that water actually get to their faucet? And so engineering really brings to the students relevance to their day-to-day life. And beyond relevance, engineering is really that problem-solving side that we want to work with the kids on, that really deep critical thinking, problem-solving piece, where we've learned something about the world through experimentation and practice, and through the practices, and then we want to now use that information to solve a problem that we see around us. And so a great example of this back and forth relationship would be when we're learning about heat and heat transfer. That can then be taken to an engineering level in the classroom by looking at different types of insulation, and how do we use this, how do we engineer solutions to the problem of either keeping heat, keeping a room warm, or keeping a room cool, or with jackets or clothing or lunch boxes, or any of these different things that are relevant to the kids' lives, that they can really see where this scientific information is relevant to them, and where this process of learning can be turned around to a process of problem solving, and there can be this back and forth. And while we're doing this back and forth, we're always going to be using math and analytical kinds of thinking. That's just a total inherent piece of it. Math is almost like a language that we use within both of these processes to really understand things and to measure and analyze and look at things. But all the while, we also need technology. There's lots of technology that we use in both sides, engineering and science, to either measure or learn or gather data, or actually just set up a system where we can gather data. And the funny thing is that all four of these pieces actually build upon each other. So as we learn more in science, we actually learn more that helps us build, create, solve problems where we develop better technology. And as we get better at math, we become better at analyzing different systems in science, and also get better at being able to engineer solutions to problems. I mean, this process, this STEM process that we hear about all over the place, is super important to our classroom. And if we can get the kids to be able to, our students, to be able to use sciences to learn about the world, but also use engineering to use that information to solve problems, and all the while incorporate technology and math into how they're doing this process, we really get a four-pillared STEM classroom that's going to work great for the students, and they're going to really see this relevance and become great problem solvers. So engineering has a process that's very similar to what we had with the process of science that I showed you, just that three-stage process. Identify. So with engineering, it's more about identifying what the problem is, and then designing some sort of solution to that problem, and then putting that solution into action. Now, if you were to look up the engineering design process on the internet, there'd be a lot more steps in this, 12-ish steps or so, but really it can be kind of simplified down to, let's identify what the problem is, design a solution to it, and put that solution into action, or test that solution. So going back to our diagram here, there is this back and forth relationship of, we can take kids when we're planning instruction for the new standards, which this is actually a good point to bring this up. I want to make sure that everybody's clear that the new standards are not, that's not our instruction, that's not what we teach. The new standards simply state this is what the kids should know and be able to do, and then it's up to us to create instruction that fits best with that. Okay? The new standards do not tell you what to teach, and they will not tell anyone, and they'll never be that way, because the standards, the definition of a standard is this is what the kids should be able to know and do. And so once we know what the end game is, once we know what the standard is, this is what we need to get the kids to know and be able to do, then we can start to create and plan instruction that will get them there. And a great process for doing that with the new standards is this gather, reason, communicate, and then identify, design, and test. And so we can gather information about the natural world, make some sort of reasoning about that phenomenon, and then communicate that back to our peers multiple times, going through this process a bunch of different times. But then at some point, we're going to probably be posed with some sort of a problem, like how do I keep my house cool? And then we've got to identify what that problem is, design some solutions to that problem, and hopefully let the kids in some form or another test a solution to that using some scientific information that they've learned. They can go through this whole process. And so I'm bringing this up in this video just because I think it's a great process for you to think about in your planning. So what kind of activities or what kind of lessons or episodes will we create that are going to have the kids gather, reason, and communicate? And after they've done that a few times and we've started to identify a human problem that we can solve, let's take them through this engineering side of it, of identifying the problem, designing solutions, and testing those solutions, and bringing that relevance to the classroom. All right, so hopefully by now, getting back to this what is science to your students, you will have had, you'll start to really see when we're talking about this three-dimensional approach to science that it's a bit different. We're looking to integrate all three pieces together so that science can be a way for the kids to learn about the world, but that science can't stand alone. It also needs to be brought to that level of relevance using engineering, where they start to become problem solvers using the information and the processes we've gone through in science. And during that time, they'll also have increased their math skills and used technology to support these things. So, when we do the gather, reason, communicate process in our planning, we should really be thinking about what does that look like. Now, gather, reason, communicate could take various forms. It could be reading and then classifying the information we got from the reading and then writing that back out in some sort of graphic. It could be the gathering could be testing, and then the reasoning could be some sort of analysis of our data. And then the communicating could be diagramming that data in a graph of some kind and explaining it, or just explaining it to somebody. So it comes in a variety of forms. That gather, reason, communicate process. So as we begin to plan for the new standards, it's really important that we actually get a solid understanding of the framework of the new standards, and how do we take those new standards and then create our instruction from that. Okay, so during this module you've learned a lot about thinking through maybe like a storyline mentality, where we've broken up the class into lots of different learning episodes, and each of those episodes has a purpose of getting some bit of information or some part of the story to where the kids will be able to get closer and closer to that root question. So the root question in the new standards, that's something that you cannot Google. It is a kind of overarching question that we want the kids to be able to answer. And if you asked your kids to answer it, everybody's answer would be slightly different, but all kind of in the same general direction. But there wouldn't be a direct answer to it. Now, that's our goal. So each grade level has 4 to 5-ish root questions. And so those are really our goals, for the student to be able to understand those. And on the road to getting to that goal, so as we go through our different storylines, we're going to hit these different performance expectations. Now, the performance expectations are what you could call kind of an assessment target. They are what the kids should be able to, or the student should be able to know and be able to do at a given point in time throughout the school year. So if you're on root question 1, performance expectation 1, 2, 3, 4. So as you're getting closer and closer to answering the root question, these are kind of like benchmarks or checkpoints along the way, where kids should be able to know and be able to do something. And they're called a performance expectation because it's not just what you should be able to know. Kids shouldn't just be going through learning a bunch of core ideas, a bunch of content. They should be also practicing their scientific skills, and they should be able to do different performances based in the content at different points in time during the school years. That's what the performance expectation is. Okay, now remember, that doesn't tell us what we need to teach, but what it does say is that the kids should be able to do this and know these things at this point in time. It doesn't tell us how to teach or what instruction should look like in our classroom. So we will then, as educators, create storylines or basically classroom experiences that we put into a sequence to get the kids to a point where they can perform at that expectation. Okay, so if you look over on the right over here, it says the student's understanding of the root question progresses during these storylines, and this is via the students practicing science in the context of the core ideas. So they're learning the content, but also learning that content via practicing different science skills, and by examining this phenomena in terms of the cross-cutting concept. So by looking at it in terms of a system, if that's appropriate, or structure and function, or scale, proportion, and quantity, these different things. And so really starting to kind of look at the phenomenon you're looking at in terms of those things. So that's a basic idea of the new standards and what we should be thinking about with planning that. And you're probably thinking to yourself, now in order to do that, there's a lot of information I'm going to need then. And that information will be as supplemental material in the new standards. And so this is 6th grade. We have root question 1, how does energy affect the structure and behavior of matter? That's what we want the kids to be able to answer, okay, in some form. And then there's a bunch of performance expectations underneath that. And if you look at those, you'll notice that every single one of those has a distinct practice and a distinct core idea present within it, okay? So in 6.1.1, we want them to develop models to describe the atomic composition of simple molecules and extended structures. So they need to be working on modeling is the practice, while also describing the atomic composition of simple molecules and extended structures, which most people would look at that and say there's a lot of stuff under there, and that is true. And so the supplemental material will kind of break this into more of its pieces for you so you can see the underlying structure. So for that performance expectation, there will be a clarification statement and also a boundary statement. So the clarification statement says basically that this is exactly what we mean by that in terms of content. Okay, so emphasis is on understanding of the difference between atoms and molecules, developing models of simple molecules such as water, and other things. And then it has an example of molecular level models could include drawings, 3D structures, or computer representations. So that's pretty clear on what it's asking. Now, there's still a little bit of fuzziness to that, and so that's what the SAGE boundary statement is. It says the SAGE test will not include these things, and so don't talk about these because it's not appropriate for the level that you're at right now. Because all of these performance expectations are based on kind of scaling of disciplinary core ideas. So going from kindergarten to high school and what things should be learned at kind of what time frame so that everything builds appropriately. And so you always want to look at, when you're planning, the clarification statement and the SAGE boundary to get a clear idea of what your core ideas are. Then you'll also want to look at the 3 dimensions of that performance expectation. They'll always be clearly stated in the supplemental material. You'll have a clear core ideas statement, and a clear science engineering practice statement, and also a clear cross-cutting concept statement. So basically saying these are the things that are kind of focused on within this realm, within the information that would be underneath this performance expectation. So once you know the 3 dimensions that are present, and you also know, kind of a clarification and boundary of where you're at within your information, then you can begin to plan instruction that will get your students there. And it'll be a 3D based planning, because you'll be thinking about what should the kids be doing What should they be practicing science skills wise, but also what should they be learning in terms of core ideas? Okay, and then the last main question here, hit 30-minute mark on this video, and I tried to make it short, so I'm going to hurry. The last question is, do we have enough time for all this stuff? And so I wanted to give you a quick look at when you're planning for instruction, what the time frames kind of look like. Okay, so currently right now, 6th grade has 4 root questions, 20 performance expectations spread across those. So that's about 7.5 hours per performance expectation in class. That's at 150 hours a year, which for the elementary grades, that's about an hour 4 out of the 5 days of the week that you spend on science. So if you spend less than that or more than that, you can adjust that, but it's about 7.5 hours per PE. And so you have 7.5 hours to take the kids through experiences that will get them what they're supposed to know and what they're supposed to be able to do at that benchmark or at that checkpoint on their road to kind of understanding the root question. 7th grade has 5 root questions, 27 performance expectations, and 8th grade has 6 root questions, but also 27 performance expectations. So those are spread out a little more than they are in 7th grade. So, and some root questions will have more than others, and so this is an averaging that I'm trying to show you here. Okay, so for 7th and 8th grade, that comes out to about 5.5 hours per performance expectation, which for most schools is about a week, maybe barely over. It's about a week, maybe touch over a week to go through one performance expectation. And remember, the performance expectation, they all kind of link together. There's not a breaking point at each PE. They kind of flow with each other, and those are just the checkpoints along the way as far as what should the kids be able to know and do at that point. You will not be able to plan out your instruction just based off the PE, though. You have to get the underlying information in order to come up with what are my core ideas, sequences, what practices we will be focusing on and going through, and what are the underlying cross-cutting concepts that we really should be looking at when we go through each of these areas. Okay, so I hope that helps you get a little bit more understanding of the purpose behind these new standards and kind of the mentality to be in when you're thinking about planning for instruction. And I hope you enjoy the rest of the module. Thank you.